welcome to Chapter 2, Section 2. So today we continue on with derivatives. However, I want to show you some shortcuts. So last time we were talking about the limit process, which, as you know, there's a lot of algebra involved, kind of tedious. Let's look at how to do this better. The first rule is the easiest one. It's this constant rule. So the constant rule just means if I'm trying to find the derivative of a constant, so a constant being just a number, there's no x's in it, then the derivative would be 0. So what it looks like as an equation, if we have like y equals some number 7 or something like that, where 7 is the constant, then if we were to graph that out, you would just get a horizontal line, and the slope of a horizontal line is 0, so the derivative is just 0. That's all that's saying. This next rule is probably our most useful rule. This is called the power rule. So any equation that you have, any function where you have like x to some power, we've been doing this using the limit process up till now. We can do this with our x plus h, but that takes forever. So the shortcut is take your exponent, bring it out front, multiply that with your x, and then lower the exponent by 1. So let's do a few examples. Let's say we started out with x cubed. So if we're trying to find the derivative of x cubed, we would bring the exponent out front, so the 3 comes out front, x, and then we would lower the exponent by 1. So instead of a 3 as the exponent, now it's a 2. 3x squared is the derivative of x cubed. And if you did this with the limit process, you would get the same thing. Slightly different example, but same concept. If we're trying to find the derivative of x to the 6th power, we would get 6x to the 5th power as its derivative. We would move the 6 out front and then lower the exponent by 1 to get 5. Okay, so here's where we can start doing some crazier things. Let's say we're trying to find the derivative of the cube root of x. Okay, so cube root of x, we don't have exponents here, but we can rewrite it using an exponent of 1/3. So let me rewrite the cube root of x, because remember, an exponent that's a fraction is really just a radical. So if I have x to the 1/3, I can use the power rule, bring my exponent out front, so that 1/3, x, and then now my exponent goes down by 1. 1/3 minus 1 would be -2/3. Like that. Okay, but we're not done yet because we never leave our final answer with a negative exponent. If we have a negative exponent, really that's like on the bottom of a fraction, because it would flip. And so my final answer would look like this, 1/3x to the 2/3 power. In a similar process, I can also find the derivative of something like 1/x squared. So 1/x squared means that it's currently a fraction, and so I don't have like just x to some power just yet. If I see it like a fraction like this, I do need to rewrite it first. So because it's a fraction, I can rewrite this as a negative exponent. This is the same thing as writing x to the -2 power. So now that I have it in like the exponent form, then I can use the power rule, bring that exponent out front, and then subtract my exponent by 1 now, so -3. Okay, then I still have to rewrite this so I don't have negative exponents anymore. So this will become -2/x cubed. So keep in mind, only the thing with the negative exponent gets flipped to which side, whether the top or bottom it's on. So the -2 didn't have a negative exponent attached to it, so that's why it stays on top. But the x has a negative exponent attached, so that's why it went on the bottom. So the next rule is the sum and difference rules. Actually, two, they're kind of the same. If you have two like separate things being added or subtracted to each other, you can find each derivative separately and then just add or subtract the derivatives. So this is kind of nice and useful to use because something like if we had to find the derivative of x cubed minus x squared, then we can just use the power rule on both the x cubed and the x squared. So using the power rule on x cubed, we would get 3x squared. and then a minus sign because we started with a minus, and then the derivative of x squared would be 2x to the first power because the exponent would drop by 1, which is really just 2x. And then that's it, that's our derivative. So one thing to note is that with these rules, a lot of times people are like, oh, if they add and subtract the derivatives, then you can also do the same thing for multiply and divide. This is not true, so don't do that. They're completely different rules if you see two things being multiplied or two things being divided. And we'll learn about that next section. It's much more complicated than just multiplying or dividing the derivatives. So I know I just said for the multiplying, if you have two things that are multiplying, you can't multiply their derivatives. But if you have two things that are multiplying where one of the things is a constant, then you can just take the constant and multiply by the derivative of the other thing. So an example would be something like if we had to find the derivative of negative 5x squared. So negative 5x squared, the constant would be the negative 5. That part would be our constant. So when we find our derivative, the negative 5 stays. And then we would just multiply it by the derivative of x squared. So x squared, we can use the power rule, so we would move the exponent out front and then drop the exponent by 1, which gives us just x to the first power, which is just x. So then our final derivative would just be negative 10x. So for me, I actually think of it as take the exponent of 2 and instead of just moving it in front, I would multiply it by the negative 5 and then drop the exponent. So it's a little bit faster. Another example is if I had a constant of 7 being multiplied to like x cubed plus 3. Then the 7, since it's just a constant, I can just leave in front, and then the derivative of the x cubed plus 3 would be 3x squared using the power rule. The plus 3, because it's just a constant, using the constant rule, is just, the derivative would just be 0. So my final answer would just be 21x squared when I multiply everything out. I also wanted to give an example where the constant multiple rule does not work. So I'm going to do a problem similar to the one we just did, but instead of just a 7 as the constant multiplying by x cubed plus 3, I have 7x. So this is a case where it's kind of like how I was talking about you can't just multiply two derivatives together. Because 7x right here, this is like a whole separate thing being multiplied by x cubed plus 3. It's not just a constant, so I wouldn't be able to use the constant multiple rule. So in this case, for right now, until we learn more of the rules, the only way you would be able to solve this is if you actually distributed out the 7x to get 7x to the 4th plus 21x, and then found the derivative this way. So then the derivative of 7x to the 4th would be 28x cubed, because I would take my exponent, bring it to the front, and then drop the exponent by 1. And then plus 21x, since it's currently x to the first power, the exponent of 1 coming out to the front would just be 21 times 1. X dropping the exponent by 1 would be x to the 0th power, but x to the 0th power is really just 1. So my final answer would just be 28x cubed plus 21. Alright, so those are all the rules that I have. From here, I just want to do some more examples for practice. So let's start by finding the derivative of 9 over 7x squared. Okay, so first, let's look for any constants. I've got a 9 on top, 7 on the bottom, so really I can rewrite this as 9 over 7 times 1 over x squared. But then 1 over x squared, I really don't want that as a fraction either because I want to be able to have it in that exponent form. So I'm going to rewrite the 1 over x squared as x to the negative 2 power. So now I have a constant of 9 over 7. So that stays in front. And then the derivative of x to the negative 2 power, I can bring the exponent to the front and then drop the negative by 1 to get negative 3. So from here, we end up with negative 18 over 7 times x to the negative 3 power. But of course, we don't want negative exponents in our final answer. So this will end up being negative 18 over 7x cubed. Here's another example where we have to kind of manipulate our original problem first before we can find the derivative. So if we have to find the derivative of 3x raised to the 4th power over 8, we can't just find the stuff inside the parentheses. We actually need to simplify this out first. So 3x to the 4th power is really 81x to the 4th. And then from here, we've got a constant of 81 over 8 being multiplied by x to the 4th. Okay, so from here, this makes it a lot easier. If I have a constant of 81 over 8, and then I can multiply with that derivative of x to the 4th, which would be 4x cubed, then my final answer is going to end up being 81 over 2x cubed. Or if you want to write it as 81x cubed, that way you kind of keep track of whether your x's are on top or they're on the bottom. Okay, another one that I want to do is if we had the square root of x plus 3x squared. So just keep in mind, our radicals can be written as exponents because a square root is the same as saying x to the 1/2 power. So now I can use the power rule. X to the 1/2 power, I'm going to bring the exponent out front and then subtract by 1, because 1/2 minus 1 is negative 1/2. And then with the 3x squared, I've got a constant of 3, and then multiply that with the derivative of x squared, which is 2x to the 1st power. So from the 1/2 x to the negative 1/2 power, that'll end up being 1 over 2, and then x to the negative 1/2 power ends up becoming a denominator because of the negative exponent, and then plus 6x. Okay, last one. It's going to look a little crazy. We're going to have to take the derivative of x cubed minus 3x squared minus 5 over x squared. So we kind of talked earlier about how we can't just find the derivative of the top and divide it by the derivative of the bottom, because that's not how our rules work. It only works for if we're adding or subtracting. But I noticed I only have one term on the bottom, so I can technically divide everything on top by x squared. So if I do that, then let me write this out. I can write it as x cubed over x squared minus 3x squared over x squared minus 5 over x squared. And this only works because I only have an x squared on the bottom. If it was like x squared plus 1 or x squared minus x or something like that, once you have two terms on the bottom, then you can't do this. So we are lucky here where we just have the x squared on the bottom, so we can split up into multiple fractions here. Because once I split it up, then I can simplify all of these. X cubed over x squared is just x. 3x squared over x squared is just 3. 5 over x squared can't simplify anymore, but I can rewrite it as 5x to the negative 2 power. Okay, now finding the derivative of each thing. Derivative of x is just bring out the exponent and then drop the exponent. Negative 3 is just a constant, so the derivative would be 0. And then minus 5 times the derivative of x to the negative 2, so bring the exponent in front, drop the exponent by 1. So finally we have plus 10x to the negative 3, so this would be 1 plus 10 over x cubed. Alright, that's all I got for this section. Thanks for watching. Bye.